I am Matt Lancaster. I lead software architecture for Accenture for basically our software innovation and cloud-native applications work. And in that vein, we've come up with some really interesting stuff that we're calling Rhythm that we're going to talk to you guys about today. And then I have my colleague Eric here as well.
My name is Eric Motazity. I'm currently leading up the aforementioned Rhythm. We'll kick it off.
Alrighty. So, what is Rhythm, right? What is this magical stuff we're talking about here? So, we are taking broadly a serverless architecture, nice overall event-driven architecture. We're injecting TensorFlow into Lambdas and doing some really interesting stuff with that around location, motion, and intent. So essentially, this is the first and last time I'm going to read off of a slide, but I kind of like the statement of how we put this. So we're combining observations and context to identify and act upon behavior, right? And really supplement the natural flow of human behavior. And we'll get into a couple of actual business cases and what we're doing, and then actually get into the architecture and all that as well. So what is this at a high level, right? So of course, everything's on AWS, otherwise we wouldn't be here, right? So the first step is location. And even though our title says location, I think location is actually, it's a very interesting part of this, but it's ultimately a very small part of it. We did do something kind of innovative there, which Eric will talk to you about on how we're doing it. We're quite a bit more accurate than the other indoor positioning systems out there. But we're taking that location information, taking it in currently like 2-second blips, seeing where you're moving, what your motion is. We're combining that with a bunch of other information in real time in order to determine intent, right? We're doing all of that in those under 2-second increments so that we can notify other actors or take actions and events on your behalf. And we'll get into quite a bit more of that. We want to provide context and take action for interested stakeholders. So what does this actually do, right? Why does it have value, what we're doing? And I think that can be boiled down into these three areas, right? We're able to observe behavior. We're able to use machine intelligence and sort of the correlation of all past actions to determine intent and provide context. And when we're talking about observing behavior, thank you for the traditional phone ring back there. We're trying to observe behavior. We're not talking about using traditional beacon solutions, right? In hospitality especially, there's a lot of these beacons all around. And what they actually do is trilaterate your signal, use your device's bandwidth if you have the loyalty application open, and you have to have it open for it to work, right? Take your device's bandwidth, use your processing power, and use you to tell them where you are. Most of the time, they don't actually have any actionable intelligence out of that because once it actually gets to the place it needs to go, you've already moved on 20 seconds later from the position you were at. So we're doing something a little differently in how we're actually getting the positioning and sort of correlating those moments of interaction. We're not using rules engines and sort of batches and queues throughout the whole system. All of this is streaming-based, event-driven, and we're taking those actions and correlating everything and moving it in real time, right? And then when we're talking about providing context, we're using that intelligence to actually do that and use non-traditional interfaces most times to actually provide that context to people. So earpieces, other things like that. We don't want people to look at a screen, right? So why would we be able to do something like this now? Insert shameless plug for AWS here. A lot of the services that we actually have available and are able to use and build a serverless architecture that allows us to do this, are really something that has only come up in the last year or so when we've been able to put this stuff together. So let's start to get a little bit more specific with what it does, and then Eric will take you through the components in the architecture. So I'm going to use a hospitality use case, but this is by no means the only thing that we're doing with this kind of stuff. I have some clients right now that are interested in this for mine safety, for industrial safety, for a lot of different use cases where getting all that information together and providing people context in real time is really important, right? Where a human can't keep track of everything that's going on. But in hospitality, our usual use case, right? Before we go through this, our usual use case, and I think all of us have experienced this many, many times, right? You're tired, you get off a plane, your plane's probably delayed, just the law of parsimony going on there, right? You get into the hotel, the doorman might open the door for you and say hi. You walk up to the front desk. The person at the front desk stops playing whatever game they're playing on their phone. They look at you like, why the hell are you here? You hand them your ID, credit card. They punch some stuff in on a green screen, right? And 5 minutes later, you eventually go up to your room, and your room is pretty cookie cutter, right? It's in many ways the current hospitality experience because none of those people know who you are. Nobody can intercede on your behalf. They don't know your preferences, right? So what we're trying to do with Rhythm is a little bit different in that we have your average business traveler starts walking toward the hotel, maybe just got out of her cab, right? She has the loyalty app on her phone, so we know her Bluetooth ID. We can do other radio signals, but we're concentrating on Bluetooth for this right here. We know who she is. We know that she has a loyalty status of platinum, and we know that she's going to check in today because she's got a reservation already. We've looked at those systems, so she's walking toward the front door of the hotel. Her intent at this point is pretty obvious to us, right? So the system checks her in, sends the key to her phone. When she walks up to the doorman gets a message through his earpiece. He says, "Hello, Jane, thank you for being a platinum member. Your key has been sent to your phone." You walk straight up to your room. Your room may or may not have whatever loyalty gift you choose already in it, right? Because we know that it's set to the temperature that you want, et cetera, et cetera. There's a lot of different events that ultimately can be processed here. And Eric's going to take us through a lot more of the sort of complexity of how we're doing this and how we're taking a lot of the null events and making sure that people don't get a million messages when people are walking near them, right? And that's one of the most important factors here is that the null is the default use case for us rather than the actual event itself. And Eric will shed a lot more light on that. So how does it work? Right, what's actually going on? How are the pieces working? So we have our traveler with the mobile device. They walk toward the door. That we see the intent and motion that's happening. They're walking toward the door, right? They get the Rhythm devices, which are devices that we're placing around. Eric will tell you a little bit more about those as well. They find they basically find the Bluetooth signature. They figure out where the traveler's at, send it to the cloud component. We get all that nice correlation happening. Rhythm is identifying the behavior. It goes, grabs data from external systems, and then as she's walking up to the doorman, since the system now knows that she's checking in that day, it sends a quick audio signal to the doorman with her name and loyalty status so that he can give her the proper greeting. He never has to look at a device. He doesn't break the sort of hospitality rule of how their business works. And it becomes a very natural human interaction, right? So at this point, we're probably sounding like we're selling magic, right? Or possibly a little bit of snake oil. So in order to not do that, Eric is going to actually take you through the components, and we'll show how everything actually comes together to work.
So basically, the Rhythm platform is composed of 3 distinct areas. There's passive signal sensing, where we take in different radio frequencies, specifically in the 2.4 gigahertz spectrum. Currently, specifically, we do Bluetooth Low Energy and then Bluetooth Classic. We have our Rhythm Ephemeral Cloud, which is a mostly serverless infrastructure. We do have some things, we have some GPU instances running that aren't technically serverless, but we do make every effort to do everything as serverless as possible. And then everything culminates in what we call natural interactions. So the idea of Rhythm in the beginning was to basically take humans and machines and make them work better together, especially in an employee environment. More often than not, we do this thing where we focus on our customers as opposed to the people that are actually servicing the customers.
And when he says we, he means most industries that are in the service business, right?
We as in technologists and marketing people.
Exactly, right? We're focusing on the end customer rather than focusing on the employee and empowering the employee, which is what we're trying to flip the script on here.
That's right. So by taking the focus off the customer, we're able to apply some of the new modern patterns and other ways of working towards that employee. So natural interaction is one of the most important things that we identify. So employees work, especially in the service area, they don't work with UIs. And we say UI, I mean visual UI. More often than not, they have to make things like eye contact, can't look at a watch, right? That is a different social connotation. So we do everything as natural as we can. So if the natural interaction is audio, then we'll push everything audio. We'll do bidirectional conversations so that the employee can talk, and Rhythm will listen and then push audio the other direction as well. If it is a visual UI job, which those do, I mean, I work with a visual UI every day, then visual UIs. And we also support API integrations with external systems as well, if you want to do SMS or whatever it might be. Sorry, I had to figure out how to advance the slides. So the Rhythm devices themselves are ultra low cost, multi-purpose hardware. There's two main considerations when we started building them. The first consideration is that essentially it had to be ultra low cost, almost throwawayable. So we can build them with commodity components and sell them at retail prices of sub $20, which make them extremely easy to adopt. If they don't work for you, throw them away. And the solution's purely additive, which means that because it's all running serverlessly on AWS, if you don't like it, you can just get rid of it. It's not part of your infrastructure itself.
And on the flip side of that, right? When you look at the economies of scale for a lot of the beacon stuff we were talking about earlier, those are several $100 devices in many cases.
For the enterprise ones, at least.
For the enterprise ones, it's quite expensive, and especially in the hospitality business, because since we're using that as our main sort of anchor use case here, most of the hotel properties are owned by owner-operators, right? They're not owned by the big brands. The owner-operators have a very razor-thin margin. You ask those folks to spend $20,000, $30,000 on something that may or may not work, you'll be lucky if you get out of the room without being tarred and feathered, right? But if you're giving them something where you can say, look, I can enhance what you're doing right now and enhance a lot of the sort of human interaction that you have, and what it ends up costing you is a few $100s worth of devices and some AWS compute.
So the devices themselves, other than being lower cost, they were built to be ubiquitous. So we have everything from signal sensing on board. We also have bidirectional audio support. So via OTA, over the air, we can alter the firmware on the fly and essentially transform the device and have it take on a different persona in the organization. Currently, we do only audio and then obviously signal sniffing, but there's theoretically no limits, provided they don't require massive amounts of CPU usage. Our passive signal sensing is pretty interesting. I think that was one of the first things that sort of set Rhythm apart. If any, I don't know how many people here, actually a raise of hands, how many people here have done a beacon implementation? Okay, good.
Decent amount.
So in the traditional beacon manner, right, everything's based on distance. And there's sort of two ways that a beacon can work. It can be proximal, so your distance from that beacon, or via trilateration to an attempt to position someone, where you take three distances, draw three circles, where those circles meet is theoretically where you're at. There's two fundamental problems, as Matt talked to earlier. The very first one is that you're relying on the person's device to do all the processing. So essentially, your phone does the processing, it sends the data up to the cloud, and the end result is more likely than not, they send you a marketing message. So you're basically paying with your battery and your data plan to get marketed to. The second major issue with that is distance works great outdoors. When you get into an indoor environment, when you're relying on a known TX power, which is your transmission power, and a known receipt power of that signal itself, if there's any obstruction or anything that would permute that signal, like we have lights and metal all around, they all act as a signal permutation. All the bodies in here will actually cause a drop in that signal through every body it passes in. You can't get a reliable distance. So what we decided to do was take a completely different route and dump all concepts of trilateration and also take the work off of your device. So we sniff in a few hundred times a second all the signals in the 2.4 gigahertz spectrum, and we take those signals, we push them up, And then that is actually combined together and using a neural network. It's basically just a recurrent neural network that runs through and understands what things look like in an environment. So we take samplings all over an environment and then take those measurements. We also use a Hall sensor on board each device to detect electromagnetic interference. So as lights go on and off, we can actually detect the different variations in the environment that can actually affect positioning to get you down to basically about a meter accurate.
Which for reference, most GPS is about 3 meters, right? My morbid story on that is that's why the blast radius of drone strikes has to be so large, because they're positioning you only in a fairly large area, right? So if you think about trying to do a little morbid example, right? But if we're talking about positioning people in an interior area, 3 meters is worthless, right? Because you need to actually have some amount of accuracy to see whether somebody's actually walking toward the front desk or whether they're walking toward the elevators, or et cetera, right? If you get it down to about a meter, that's about the width of my shoulders, right? So that's generally one person. We can probably get it down a little further in further iterations, but I think it's 3 times better than what has been done before, which is one of the interesting things here.
Yeah, just a disclaimer, of all our use cases, we don't have indoor drone strikes, but
2.0.
Yeah, I don't know. So the Rhythm Ephemeral Cloud itself is mostly serverless. So we use lots of kinesis. We have an architecture diagram that we'll show a little bit later that goes a little bit further into how we do it. But essentially, everything, if we can, we make serverless. One of our big issues when we started was that anything in the machine learning realm, whether it be TensorFlow or whatever you might be using, tends to typically run on dedicated hardware. So we actually have an open source project, which we'll share with you in a little bit, where we're able to bake TensorFlow and take over the Lambda environment and have that execute ephemerally within Lambda so that we get pure horizontal scaling and massive savings in costs over. We still do our training on GPU instances. We haven't found a way to use Lambda for that, but outside of that, that's about all we do. Natural interactions is sort of the crux. It's what we're trying to do. So the culmination in these, what we call opportunities for interaction, result in the communication from rhythm to whatever that end user might be. And so like I said, we will listen to bidirectional audio, so you can talk to it, it will talk back. And Matt kind of talked a little bit earlier about this concept of nothing, which is sort of, when you talk about natural interactions over audio, one of the last things you want is a chatty interaction. It's the easiest way to get an associate to pull the thing out of there and throw it away. So it's one thing to have things pop up on your screen, which is annoying enough. It's another to have them speak into your ear. So we have this concept that we call nothing, and 90% of all of our training information, as we identify these opportunities for interaction, is actually this concept of nothing, where we actually find normal interactions or movements of people or populations within a space that indicate that they're just moving and behaving normally. And so we were able to reduce our false positive rates by orders of magnitudes of well over 100 less. So I think we're down from, we were getting, when I originally did it, I set my whole house up. And my fridge, because I didn't really have a check-in desk and it doesn't really exist at my house, my fridge was sort of my opportunity for interaction. And so I was having 100 false positives as I would walk by my fridge, that I was going to my fridge, as opposed to I'm walking up to my fridge and then I'm egressing away from my fridge. And so by adding this concept of nothing, I was able to get it down to 1 false positive and about 200.
All right. So when I mentioned earlier that we're a deeply event-driven architecture for this, right? Which means that we have a lot of opportunity for extensibility. So API integration into sending things like SMS. If any of the Twilio folks are in the room, shout out. Doing more natural interactions with different interfaces, et cetera, different types of earpieces, different UIs, right? Different types of things, or actually integrating into back-end systems in the actual business, right? So when I talked earlier about being able to, as the person was walking up, we know that she wants to check in. why make her go through the whole ceremony of checking in at a desk when we can just have the machine do it, send it to her phone, because many of the hotel properties today are installing locks that are opened by a mobile device, right? Or special keys, which you can get printed out and just walk in and grab it, right? So we very much took that concept and called into the APIs of a lot of those back-end systems, able to do a reservation, able to add or subtract loyalty points, things like that, right? So a lot of interesting interactions that can go on, and new sensor inputs as well, right? So not just motion and position, but also temperature and other things that we can feed into the system to make better and better decisions, right? If I put in my profile that I personally like to sleep in a freezer when I'm in a hotel room, so I like it at about 60, 62, 63 degrees. So give them a good air conditioning bill, and I'd like my room to be like that when I get in there, right? So if I'm walking toward the hotel, why shouldn't it also once it's checked me into a room, set the temperature in the room, right? Lots of little stuff like that can add value that you really don't think about doing, but you end up wasting a lot of time sort of calibrating and personalizing things that we can determine your intent and do it for you.
One of the largest asks we get is existing video networks to include things like different biometric information and things like that they may be using, including our passive signal sensing. And so, like I said, as a point of extensibility, we allow almost any kind of input. There's obviously a retraining effort that's required because it's a completely different type of input, but it's certainly supported. So to kind of go into a little bit, this is a very limited bit of the architecture, but this is essentially the ingest of how we take a message coming off of all these disparate devices and then essentially combine them together. As those signals are brought in, we actually combine them. We do them currently in 2-second increments. So we call it I've gotten some goofy feedback about this name, but we call it dead reckoning, which, if there's any mariners here, is the process of essentially mapping out your location over time in increments. And so our rhythm dead reckoning system will actually take all these disparate signals that are coming off. It could be from 100 devices. We'll put them together, take things like tying MAC addresses together, identifying the strongest RSSIs received, and then integrating the Hall information that's coming off the devices live when we talk about electromagnetic interference. And so we put those together using Kinesis analytics currently. We put those together, and then we actually hand it off to TensorFlow running ephemerally in a Lambda that pulls chunked models. So we do a lot of preening and then isolation with our models to make them small enough that TensorFlow can actually ingest. Currently, we're doing we're doing 1 gig instances of Lambda. I know you can go up to 1.5, but we don't typically need more than that for one location. And then we pass them through and then hand them off to our API services so that they can either do things like communication down to the user or then grab and enrich that data from currently existing, like, let's say, on-premise systems themselves.
Why don't we go back to the last one for a second?
So I know how to go back.
There you go. So, because we should probably talk through this in terms of our hospitality use case as well. Just how all those pieces that we talked about are actually interacting within the context of walking up to the hotel, et cetera, right? So when you're...
As you can see, I get bored with use cases. I just like the technology.
As you're walking toward the hotel, right? The devices pick your signal up, locate you within the signal map that's been created and trained, sends your signal off in those 2-second increments. That goes to the device gateway. It's routed to the signal ingest stream where the dead reckoning process is happening, as Eric mentioned. We actually do the signal processing. We drop it off and actually combine it, map it, store the model. And then once we have all that information, we can do our sort of correlation activity and orchestration activity where we're taking all of the information together. We make the decision. Get the intent resolution, et cetera, process your reservation, process your loyalty information, et cetera. Can you go back one slide as well?
Of course.
So just to kind of talk through this, right? Because this is not just for this hospitality stuff. It's very much an extensible system, right? For all of this, the only real kind of magic pieces that are proprietary are the devices themselves, which are made from relatively commodity hardware, but we did do a little bit of chip design, and the actual code of how the positioning's happening, right? Everything lives on native AWS components. So when we're talking through this, there's a lot of cool extensible building blocks. So when I was talking about mine safety earlier, right? Just want to talk through that really quickly because I think it's actually a really interesting one, right? Because when we get the image of mining in our heads today, right? What do we think of? Think of probably a guy with a pickaxe, maybe some automated equipment going through an underground mine full of tunnels and stuff like that, right? For the most part, that's not really how it's done these days, right? You take a big mountain or a big area, you literally just strip it down bare. There's massive trucks, autonomous vehicles that are 60 to 80 tons driving through the location. Those don't have an actual human driver, right? They drive to the location. The ore crusher crushes a bunch of ore, whether this is iron or gold or other things. It's all done pretty much in the same way. Crushes the ore, puts it on the truck, sends it over to the ore processing system to actually either crush it or use chemicals to leach out the metal, right? And in this whole process, there's lots of people walking around and doing things, right? There's a huge, I mean, if you're coming around a corner in your pickup truck, right? Because you've just done some maintenance on one piece of equipment and you're going to your next location, and you come around that corner, and one of these big autonomous vehicles is also basically bisecting you. You're going to lose, right? It's not going to be pretty. So, and even if it's a self-driving vehicle, it can't see around corners, right? What we're starting to do there is take this information from Rhythm, take the different actors in that process, the different components that one person can't generally keep track of, and be able to know where the person in the truck is, be able to know where the autonomous vehicle is, and make those decisions on the fly so that we can either stop the vehicle or warn the person that they're about to get in a hairy situation. And the other piece to that is if there are people without the proper safety equipment on, we can notify that if they're going into restricted areas, right? Where one of this whole thing started, it was kind of a sad story where somebody walked into to clean the chemical leaching vats, right? Took his breathing mask off for just half a second because he's in a really hot area, and of course the chemicals that they're using created a gas very similar to what was used in the First World War, right? And he pulled his mask off and ruined his lungs in a few seconds, and that was about it, right? But all along that process, there were opportunities to notify that person or to notify safety personnel that person was going into an area without the proper equipment, right? So actually taking the information as far as where the vehicles are going, taking information as far as safety goes, all of that can be mapped and done with the same architecture and the same process, right? And the third piece to that would be if there's any equipment that's broken down, we can reroute those autonomous vehicles so that we don't get stoppage, right? Because stoppage, when you have something that has 100 tons of ore in it, is a few $100,000, right? It's not a small amount of money if you have to reroute something and wait an hour. So there's a lot of different opportunities and different ways to use the same technology to solve different business problems, right? It's not just the hospitality bit and the mining piece. We're talking about doing this for airlines and figuring out where catering vehicles are and things like that. So same architecture, same kind of general process, but able to inject intelligence into existing human processes.
I'm going to jump onto the devices themselves. So the devices themselves, we use a ESP32 processor. We don't use anything ARM-based, and we use a semi-customized kernel that's essentially free RTOS with some modifications. And the ESP32s that we use essentially are extremely low power draw. You have about 240 megahertz worth of horsepower on board and about 512 K of RAM, not M, but K. We have NeoPixels on board so that we can do RGB visual feedback, because it's very difficult to know if they're misbehaving, if they're connected to Wi-Fi, things like that, if they're currently sniffing the area. And then obviously we have custom lithium poly batteries to drive that. Of course, TensorFlow is sort of the heart of everything that we do within Rhythm. I'm not sure I can even count the number of kernels we have running, but it's an amazing amount of TensorFlow. I won't go too far into what TensorFlow is. But we make it all happen with Serverless Ephemeral, which is, I hope you guys will visit. There's a very small link on there on GitHub, but we open sourced it a couple months back. But it essentially allows you, it's not necessarily TensorFlow specific, but it essentially allows you to build anything in CentOS and then run it in Lambda with about 2 lines of code.
And my little art project there, teasing our friends that build the serverless framework by putting mayfly wings on it to show it as ephemeral, right? We need a better artist.
Yeah, the logo's in flux.
Than the engineer.
But what's nice about it is, like I said, it allows you to democratize and do a lot of things that you would have had to spin up an entire EC2 instance. You can now just run purely ephemerally in Lambda. TensorFlow included. We have some tutorials on there that show you how to build I think we actually have a pre-existing Docker file that allows you to build the entire process out in a couple commands. And then, like I said, 2 lines of code in the serverless framework, and you have TensorFlow running whatever your custom CentOS image is. And then as much as we can, we open source. There's obviously some things that are closed source, but we currently have open source Serverless Ephemeral, and we hope to open source some new libraries here in a few months.
And likely the hardware OS stuff as well, because once again, it's running on very commodity hardware. So what we're going to do now is actually put a little bit of proof in the pudding. We're not doing a live demo because we're, number one, not allowed to do that here. And number two, just the law of demos wouldn't work all that well. So what we're going to do is show you a canned instance of how this might work in an airport, right? And how we might actually do some interesting traffic flow analysis and actually make some decisions to improve the process.
Let's see if this works.
So let's see if we can get the screen up here. It's that one, yeah.
Oh, the law of demos.
There. No,
Nope.
Went back to the.
I swear I'm following the directions.
Try the 3 again.
Yeah, right.
All right, apparently we're not going to show that.
Yes,
So,
apologies.
if anybody's actually interested in seeing that, we can show it to them afterward, because we're not going to sit up here and make you sit through that. So we have a couple more interesting things to go through as far as the platform, but I think now I want to open it up for some questions and conversation. So any questions?
End-to-end latency. Our target SLAs are sub 2 seconds. So from the minute a message goes up, there'll be a response to an earpiece within 2 seconds if it's a legitimate. We don't have that issue. We do our, so with TensorFlow, we actually grab them in batches when we build out, just like I said, your tensors in bulk. And we pass them through 100 at a time, but we do hundreds of those a second. So there's never an opportunity for the Lambda to get cold and be recycled from the runtime.
Is the implementation in Java or
A lot of different things, but no Java.
Mostly,
as a rule, no Java.
Mostly Node.js, so mostly JavaScript.
Yeah, I can say with Java.
Neither of us are big Java guys, so there's a little bit of Go and a lot of JavaScript.
Architecturally speaking, how do you guys filter out unusable Bluetooth signals off, like let's say Fitbits or phone?
We actually don't.
We don't filter it out.
We don't filter them out, but through identification, we determine if there is actually any opportunity to interact. So we have to know who they are, for instance, or if it's just a mass scenario. If it's something like, I don't know, you need to call someone else to help out with the line that's forming, we'll use that information.
Maybe once you get that data, architecturally speaking, how do you pull the information about those devices I can see?
So we actually want that information. So when we initially build the signal map of a location, right? Because we're really plotting you on a map of how all the signals are interacting over time, which is how we're able to position you very accurately. We want those signals to come in. But if, in the hospitality example, you might have installed the loyalty app once or something like that, right? And we grab your hardware address, and then when you actually send a signal, we know who you are based on correlating you with your previous information. So we'll process a lot of those signals, and we get the ones that we want and actually pass them on for further processing. The rest of them are just kind of discarded.
So it's a little bit different than that, but you can't actually ask hardware for a BLE MAC address, for instance. That would get you rejected from the App Store, but yeah.
Can you go over the positioning again? That was pretty quick, especially how the whole Accenture helps make that work.
So you have two aspects. If you're going to divorce distance, right, mathematically from the model, you have two main issues. One is density, and the other is the electromagnetic signature of a room, are your two big issues you have in any given space, at least indoors. Hall sensors are specifically designed to essentially get the amount of electromagnetic interference occurring within a space. And then you have the actual power being delivered. We take the perspective of the different devices, because remember, they're passive, so they're actually receiving them as opposed to in a beacon scenario where it's happening the other direction. And so by taking that, each one, essentially TensorFlow is trained in understanding how a room looks on the perspective of the devices in the area. They can be on different floors. We take the strongest RSSIDs because that tells you that they are closer or at least less unobstructed or less obstructed. We take that information and the electromagnetic signature as sensed from the internet, we put it together, and then TensorFlow will say that that actually looks like it came from this place in the room. Does that make sense?
It's not necessarily not triangulation, but it's done.
You can't triangulate, because when you triangulate, you deal with angles. Existentially, you have to know where you're at in order to triangulate yourself. Trilaterate is distance.
So in theory, the machine learning algorithm could be doing something trilateration-like, but
Well, you can't, because the issue is, so for instance, if I have my phone in my pocket, I have 3 devices, let's say even do beacons, right? 3 beacons on the wall. As I move in a circle, as that signal permeates through my body, it will drop off in relation to it. It will make it look like I'm either bouncing around or making a big circle around the room because the distance becomes obstructed. His body next to me, because he's a lot larger than I am, is going to come further obstruct it. So this will make it, I didn't mean that, that sounded bad. But it's going to make it look that far. And what you have in trilateration is when you get a major drop off, when that distance looks like it decreased, if you need to draw 3 circles to know where they are, you have 2 circles that meet and a third that doesn't. You have no position or any method of getting the position other than you could say, with a very large margin of error, I'm in the room, which doesn't do a whole lot of good. So that's why we had to completely divorce distance from a positioning model and then look for a complete other way of doing it.
Why don't you go into the other way of doing it, because I think that's what the bulk of the question was.
That's like a 4-beer conversation.
how many nodes do you need to cover something like the casino floor?
So that is, the funny thing is, it actually is the density. Per rhythm device, we can sense about 250 individual MAC addresses per second. So if you get greater density than 250, that's an artificial limitation just with the equipment and the code that we're using. We optimize, we used to be 150, we're increasing. But as you go past, you need greater coverage. And that often means by segmenting the room, so putting more devices on one side and more on the other.
And just on the location, we are actually happy to talk through that with people. I just generally follow the Hawking principle of presentations, which is every equation that you have, you lose like half the room, right? And there's a lot of math involved there. So we're very, very happy to talk about it afterward and go in great detail. But it's very difficult to do that when we're standing up here.
Especially when you get with unscented Kalman filters and things like that.
Yeah.
It gets pretty nerdy pretty fast.
So.
How many devices did you have to manufacture to get the cost of that?
That's actually not at bulk.
Yeah.
It's sub 20, not at bulk. I don't know what the real number would be at bulk.
So the funny thing is it's actually including his labor cost, right?
Yeah.
In that. So he actually
I built them in my
manufactured all of our
garage.
current devices in his garage. And then we did some more at one of our offices in the Bay Area, right? So it's very expensive people putting these things together right now. we're going to get a contract manufacturer. Our whole deal here is not to go sell devices, because I really honestly don't care about that. I care about the total solution of how we're able to solve some of these business cases. And the devices being really inexpensive really helps with that, especially for like the hospitality stuff I was talking about.
So you kind of answered my question just now. When can I use this and when can I get advice?
Sometime 2018.
Come up here afterwards and let me get your email address and we can talk.
How much time do we have, just out of curiosity?
20 minutes. We got plenty of time.
Oh, well, let's go to town.
Can you speak up just a little bit?
It's supervised and unsupervised. So when we start it, it's purely supervised. So we take a critical mass of what we know about the room, including how signals move throughout the room. And then over time, as populations move in and out, we further refine it. Yeah, we have a system that actually spins its own training back up once essentially our models become, the delta becomes high enough that it's different. It'll retrain itself and apply it. The deployment? Well, it runs in just AWS serverless components. So, I mean, those could run in a VPC if you really had to have them. But outside of that, I mean, one of our main design ideas was to make it purely, people talk about transformative as being this wonderful thing in an organization. Transformative is a massive interruption in an organization. An additive solution is something that you can put and interop with those current, probably nightmare systems that exist within their organization. So we wanted to make a purely additive solution so that we had to have as few hands in your internals as possible.
Put my consultant hat on for a second. I think that, so we very much tried for a strategy of, and succeeded, tried for a strategy of evolutionary rather than revolutionary, right? As Eric said, additive, right? So, you know, evolution may occasionally be a painful process, but revolution tends to involve guillotines, right? So, you know, and you have a very high chance of failure when you're trying to change a lot of sort of sacred calves of business processes. When you build things and sort of augment existing processes, you can often get into this nice learning loop where you end up with the same end result as if you tried a big transformation effort, but you do it in a very incremental fashion. So it's sort of like the boiling the frog thing, right? People start to have their process augmented, and then a year later they're suddenly in a completely different process, and they're totally fine with it because you did it in tiny steps. So this gentleman's been waiting for a little while.
Yeah. Can you talk more about the intent mapping, how you balance short-term and long-term memory as it relates to intent mapping?
So when we talk about intent mapping, I'm not sure I would use the word intent as much as it's an opportunity for interaction. I only say that because intent has this, like all these other connotations that, especially if you're in marketing, becomes this recursive argument. But what we do is when we're doing our dead reckoning, right, we take a position, we take another, we take another, we take another, and over the course of 6 positions, which is about how many we ever do at any one time, we determine sort of a pathway of movement, and then we also take into account all the other movements going on around. And then we have essentially a training system where, like I said, that purely supervised part, we actually define where your opportunities for interaction are. So you would say, here's my front desk. This is what it looks like when people walk up. This is what it looks like when someone walks away. This is what it looks like when someone walks by.
Right, but you have to balance the, hey, I'm walking up, say, for the first time to the hotel, or hey, I've been there earlier in the day, right? So how do you balance those 6 positions with knowing, oh, hey, this person's already been here?
That's actually part of when we go to fight. Like I said, I think it kind of actually goes into his question a little bit as well. When we take all this information in aggregate, we are aware of the past actions. So if we've already checked you in, we won't check you in again, right? But those things fire thousands of times a second in a given, and we check to see if an action's already been taken on that behalf, or if there's actually a better action to take. Just because you're walking up the front desk, we may not say, you know, John Smith is walking up to the front desk. We may say...
It's part of the magic of being able to correlate with all that other data, right? Once you've already checked in, we know that. So if you're walking toward the front desk and you stop, and you're waiting there, you might actually want to interact, right? If you're just walking by, you've already checked in, so you fall into the null case. So it's pulling all that information together. Positioning is just one crucial piece of it.
This is related to the filtering question that we had. You guys said that the filtering happens in the cloud, like off the noise.
Yes.
The question is there a lot of unnecessary computation that's happening in the cloud, and how that is impacting the cost? Because that
It's incredibly cheap. It's one of the reasons we go the serverless route. You're paying it, 300,000th of a cent per Lambda execution. We do those in bulk. We don't do one-offs. So we pull that information off of a stream. We may process 100 to 1,000, depending on what the load currently looks like. And executing off that, it's wildly cheap.
okay. Like my question was, does it make sense to drop the signals at the device?
No, because then you get into the design consideration of, I'm stubborn, I'm still trying to make this work. You get in the design consideration of you need a lot more horsepower on the devices, and then now you have to have all the devices talking at the same time. So now you're mesh networking the devices, which means you're increasing latency, and you're increasing latency away from the place where the decision's actually made, which one of our design considerations, we wanted one hop from the device to a decision to get it under that 2-second SLA mark. Go ahead, you can get it first.
Have you had any issues with the amount of data that you have to send from your devices up to the cloud?
That's a goofy story. We had one issue once, but that's fixed. We had an issue where it was literally hitting it every time. The device gateway on AWS, it would hit it every time it sniffed an address. And we actually shut down a corporate Wi-Fi 4 or 5 times before we figured out that was what was doing it. Yeah, it was really bad. So, but since then, we actually do things in bulk. We spin them up. We do some memory management to push them up, and we haven't had those problems anymore. We also moved to a more binary protocol away from what we were using before.
All right, just a couple folks over here, so go ahead.
So I don't think I quite grasped the difference between the triangulation and the trilateration. And we had a really good example about how it didn't work. I just couldn't grasp.
So we don't actually use either of them. The example is really that those don't work, right? If you're positioning with angles, you have lots of margins of error, and as Eric said, if you just basic interference from having something in your pocket, the trilateration is going to have real problems in an interior space. One of the other cool things that we're doing here that we didn't get to show is sort of modeling the whole 3D space, and we can, if you can imagine like in a command center, you can actually see folks walking through, and you can see the paths and stuff like that. So it's one of the big things we're trying to do with an airline airport clients is how do we control traffic flow? How do we know how many folks of a certain loyalty status are on a certain plane? If they're in terminal A and they need to go over to terminal D, do we need to delay that plane? Because there might be 2 people on that plane with no status that might miss their connection, but we don't want 15 people with the highest status on this other aircraft that are going there to miss their mark, right? And there's hundreds of these things going on at once, and no person in a command center can actually make those decisions, and that's where all the machine intelligence coming together to actually pinpoint actually starts to add real value.
I think what I can't get my head around is like you've got 3 Hall sensors.
Mm-hmm.
How do you do it without triangulation?
If you have 3 what?
You got 3 of those sensors with our little Hall sensors trying to like.
Well, there's more than Hall. Hall is just one factor. We do Hall. The Hall sensor is important because it helps us do things like you see how there's communication devices in here, things like that. They artificially alter the electromagnetic signature. And so when we train on locations, we don't want to just know what the power received from a signal was. We also want to know what's going on in the room.
So you can almost imagine as we're calibrating and understanding all of these signals and signals over time in a room, we create almost a treasure map of locations in the room. And we're telling you where you are by virtue of where you're not and how you're interacting with those signals, right? So it's really using all of our wonderful electromagnetic interference around us for a useful purpose as opposed to just noise. Can you speak up a little bit? Actually, that's a really interesting use case. So one of the very early use cases that we had with this was, okay, you have the front desk, right? And let's say you have 3 people start to stop at the front desk, right? So what do you do there, right? So what you probably shouldn't do is just give the person all 3 names, right? It's not going to be super useful. They're going to take the earpiece out and be very frustrated. What you might want to do is say, okay, there's a queue forming, right? There are people waiting there. They're in a line. Let's call for another associate to manage the situation. And so we do that, and then they can use sort of the human interaction itself to manage the situation.
And also let the person behind the counter know that someone else is coming.
Yes, exactly. So they're
As
not
opposed to
frustrated.
It's also another interesting, it's sort of the UX of audio is the idea of not telling them what to say. I think sometimes when people imagine what it's saying in someone's ear, it's very, deliberate. You tell them this, like a lot of people that have worked in the service industry, they work there for 20, 30 years. Like they know how to communicate with people. We just give them context, a name, a status, whatever is actually important in that interaction, then leave it away.
I mean, one of the most annoying things, and I think we've all been there, right? Is somebody has to sit and look up your information, and then they pass you off to somebody else who also has to sit and look up your information. Right? So if we can just give them that information so that they can actually help you, rather than spend 90% of the time looking things up in different systems, it creates a better situation for them because they can help more people and they're finished with the interaction quicker. And it creates a much better situation for you because you're actually able to get your problem solved quickly as opposed to sitting there waiting and twiddling your thumbs.
You also don't get the who are you and what are you doing question, which is what you get every time you enter a hotel.
So it just occurred to me that you have to train this for each room, basically, or each area.
Every area, yeah.
How does that process work? Where do you get into that?
That's the nightmare. That one's a nightmare. We have a solution for it.
Yeah, we have two solutions for it, right? So one, we're actually building a little robot that will actually, and you can imagine eventually a fleet of little robots that will walk through spaces and actually map it all out, right? The other solution is using. So Eric, I'll let you talk about that one because you're the backpacks, right?
No, I'm going to go into that. That's part of our robots as well. But one thing to bear in mind, a space this large and the amount of samples we have to collect to do it right, I would say this space is probably 4+ hours to train. So that's why we're looking into actually automating that process, including adding in Google Cartographer's SLAM to actually map the location simultaneously. We build 3D views. So I was going to try to demo, but I apparently can't operate this thing. But yeah, it's like 40 buttons and they all just blink. But essentially, we map out the entire space in 3D. So if it's your hotel or your airport, whatever, the entire thing in 3D. And then you can actually see all of the dead reckoning going on within the space live. And then you can also see all the moments of interaction that are occurring through bubbles that pop up where those communications are occurring. So from a managerial perspective, that's probably the more natural way to look at your organization. But yes, it does require taking 1 meter samples, and Rhythm will tell you when it has enough, but it could take about 4
hours.
It's not
as onerous as it sounds, right? You really only have to map a location once. And right now, I mean, you can crowdsource it with people, with devices, or you can do the autonomous robot route, or there's some other things that we're working on. But even mapping something as large as an airport is something that's doable in a couple weeks. And then you end up getting the benefit long term while we're setting the rest of the stuff up, right? So there's a lot of opportunity there.
So how sensitive is the model to changes in the overall inherent nature of the room? Like, for example, let's say they decide to put a great big chandelier in the middle of this room, or a giant Christmas tree or something like that, right? Is that something that would cause you to retrain the model?
That's one of the reasons like I said, a robot with SLAM on board. If anyone's not familiar with SLAM, it's simultaneous localization and mapping. It essentially allows you to use a LiDAR, an accelerometer, and a gyroscope to move logically through a location and get all of the obstacles in the location as well. And so our bot has all those involved. So if there is a fundamental change while it's doing updates and training, then there's different scenarios depending on how different that delta is. If it's a fundamental difference, then it's a complete retrain, obviously, but, there's logic to handle that.
Adding a Christmas tree in the middle of the room is probably not that fundamental of a difference, right? What will end up happening is that, I mean, it's learning on the go as well, right? So if people start avoiding that location, and you start to see a clear sort of round piece where that Christmas tree is, we will then know that there's a new object in the room that needs to be placed.
Or like, say the hotel manager decides to, for whatever reason, rearrange the layout of the furniture in the lobby.
Yeah, if they fully rearrange a lobby or fully like remodel something,
It'd just be a retrain.
Then you have to retrain.
Start from scratch. It's not a panacea, but it's pretty good. Oh, I'm sorry.
How do you label incoming device with MAC address X and John Smith, the person?
So we do a process. This was a very weird thing to have to solve, because you can't ask the device for the MAC address, and then any device addresses you do get are wrong, because if you're anonymous, it will often send off an obfuscated MAC address that's not actually the one that's listed. So there is this goofy thing that happens if you have a Mac and an iPhone. You'll probably have seen it occur, where you walk into you log into both with your iTunes address, you walk into a space, and then all of a sudden, it's aware that it's there. And so we have this, I don't know how it's really working, we have this theory that it's a metadata exchange that's occurring. And so we modeled our theory on that. And so we actually do a metadata exchange when you enter a place for the first time. And so if you have, let's say, whatever that provider's app, whether it be your hospitality or hotel company, whatever it might be, I don't want to use any names, but it'll actually do a metadata exchange on first entry with a rhythm device that's sniffing, and then the rhythm device will report that up. And at that point, it's done.
Yeah, you guys talked about indoor space, but if you have a mixed indoor-outdoor space, is the solution still location?
It's still valid with outdoor, but if it's a big outdoor space, you just use GPS. GPS is it's trilateration, it's the same, but it's unobstructed mostly, right, except for clouds.
And there's no issue with using combinatory signals.
Our current devices are not waterproof, though.
And no pools.
Yeah, you wouldn't want to put them in a pool or in the rain.
Alrighty.
That it?
Oh, we got one more? It really depends on the use case, but
Our costs, 95% of our costs are GPU instances.
Yeah.
That's literally what their as training comes up.
And when we say 95%, we mean a couple $100, right? To actually train it for the location.
It's been a few hundred.
Yeah, and if you have a very large location, maybe a couple thousand, right? But the hardware and cloud infrastructure cost is infinitesimal compared to setting up big dedicated instances and having licensed software and all that kind of
Actually,
stuff.
to clarify that, when I said we did model pruning, we also do some compression on the models as well. We don't use mass models like you would normally find in a big AI. A lot of people approach AI in this very monolithic mindset, right? You have this model that does everything. Models all the we model specific areas, right? And then on the fly, we'll grab different models to keep them nice and concise. Because of that, our training is only based on a small, concise model, which means we can train. We use GPU instances very fast, and we queue them out so that we just do one model at a time to the next. But we can train an entire location like this with 100,000 points. We can do that in a couple minutes. So it's not necessarily expensive, it's just we run a lot of GPU instances.
During the training.
Some of it's me screwing around, some of it's training, but we do a lot of GPU stuff, and that's really where the costs come out, because K80s and P100s aren't cheap. Yeah, well, thank you.
Thank you guys very much.